All right, now in this lesson, we're going to take a look at reaction dynamics. So, what causes a chemical reaction to happen? Why don't chemical reactions just happen all the time? All right, so we're going to go back to the initial question. Let's look at this methane burning from a Bunsen burner equation. We got CH4, methane plus oxygen gives us H2O plus CO2. Anytime you see an equation, first reaction is to balance it. C's are balanced. O's are not balanced. H's, well, we need a 2 here. Now we got 4 O's on this side, 2 here, 1, 2, 2, 1. All right. So we can see that the reaction is a exothermic reaction, because the energy term is found on that side, the product side, which indicates that energy is being released into the environment. Right? That 802.3 kilojoules is being released into the environment, right? We burn 1 mole of CH4 and 2 moles of oxygen. We're going to get 2 moles of H2O, 1 mole of CO2, and we're going to get this 802.3 kilojoules of energy, which we can use to heat water, burn your hand, start other fires. All right, so the big question is, why does this not occur instantly? Why does the methane not burn until a striker is used over top of the methane gas? That's an interesting question. Well, let's take a look here. It's like trying to push this giant ball down to this side of the mountain. Yeah, the ball's going to roll down the hill, but there's a little upward part here. You got to give it a little push start. You got to get some guy down here, little Paul Bunyan on the mountain, to give it a little push start. Oh, there's a Greek guy who had to haul a stone up a mountain for eternity as his punishment, only to have the stone roll down the mountain. And then you had to go down to the bottom of the mountain, grab the stone, push it back up the mountain. They rolled back down to the bottom. Anyway, so we got this little guy here, forget his name, pushing this little ball over the peak of the mountain. And once he gets it to the peak, well, gravity's going to take over the rest. And you've got like the little village down here. And that little village is going to get demolished. So the spark is like this little guy pushing the ball up the hill, and then you get all this energy. Now we're going to go into detail right here with this reaction. All right, so we got 3 stages of a reaction. We have our reactants. Then way on this side, we have our products. In the middle, we have this intermediate step, and there could be many intermediate steps, activated complex. So in this reaction, we start off with our CH4. CH4 is going to look like this. We've got 1 CH4. And we've got 2 oxygens along with it. So O2, O2's double bonded together. All right, there's 2 oxygen atoms bonded together twice. Now, in order to get this to change form to our products, we have to break these chemical bonds. In order to break chemical bonds, we have to put energy in. So energy is going to come in. I'm putting it from the bottom because I got space to write. So we have to put energy in. Remember, this guy has to put a little energy in to get it to the top. Then once you've put that energy in, then you've got like the hydrogens just floating around here, separate from the carbon. You got these oxygens just kind of floating around. So you got all this activated complex. So in order to break the chemical bonds, we put energy in, they broke. We get this activated complex right here. Then this activated complex is going to reform into the new chemicals. And the new chemicals, well, we've got H2O. It's like this. H2O bonded together. There's one of them. We've got a second one of them. And then we got CO2. C, I think it's double bonded like this. Now, when these new chemical bonds formed, they release energy. So we are going to have energy coming out. So we put energy in to break the bonds. We get this activated complex, which has a higher energy state. And then we get the products where when the bonds formed, energy flows out. In an endothermic reaction, it takes more energy. You put more energy in than you get out. In an exothermic reaction, you put less energy in than you get out. So in this chemical reaction, you put very little energy in to breaking these bonds. They're not hard to break, but when these bonds form, they release a lot of energy. So a little energy in, that's the spark, gets you a lot of energy out. All right, so we're going to look at this in a diagram, a reaction pathway graph. So a reaction pathway graph has these things. It starts off with our chemical reactants at a certain energy. So right here is our certain energy. Then the reactants have some energy put in, and the energy of the chemicals goes up till you're at the activated complex. Then, as the chemical bonds form, you release energy until you get to the products. Okay, so the reactants started at a certain amount of energy. The products end up at a different amount of energy. And you have to put in energy in. So we're going to just make a note that this section of the graph right here, this is energy in. Break bonds. That's energy in. The bonds are being broken. The chemical is getting more energy. The activated complex is the most energetic state. And this part, energy out. Bonds form. Now in this particular graph, we have less energy in than energy out. That means that this reaction is exothermic. Exothermic. Less energy in than out. It's also exothermic because this distance right here is our change in enthalpy, right? We started with a high level of energy, then we end up with a low level of energy. This is our delta H right here. Our delta H is negative. That means it's exothermic. So the products have less energy than the reactants. The energy that it used to have all went into the environment. All right, so let's take a look at the second one. Here we've got our chemical energy present, and here's our reaction pathway. It's time. So we start with our reaction. Energy goes in. till we get to the activated complex where the chemicals are all broken apart. And then energy comes out till we get to the products here. Now in this case, our products have more energy than our reactants. This is showing that the delta H is equal to positive number. This is an endothermic reaction. Okay, so in an endothermic reaction, we have to put more energy in than we get out. Where does this energy come from? The environment. So we take a bunch of energy from the environment, we give a little bit back, but energy in the end came from the environment. So that is an endothermic reaction. Notice that the products have a higher energy level than the reactants. It means delta H is positive. All right, the last one. Now this guy, there's two possible pathways. Okay, so we've got the chemicals and they can go up and it takes more energy here. Takes some energy here. But in this type of reaction, if we add a catalyst, then it takes less energy. So this guy here is showing that adding a catalyst means less energy is needed. So that means the reaction will happen quicker because you don't need as much energy. Okay, so let's take a look at what some of these letters show. Okay, so letter A, this distance from here to here. Letter A. That would be the energy lost, so the energy out with catalyst. Right, it had this much energy at the top, and then it drops down to this much energy at the bottom. So with the catalyst, it loses that much energy. B, right here, letter B, is energy in with catalyst. Now we call this the activation energy. That's the amount of energy. So B is starting here to here. The amount of energy we have to put in to kickstart this reaction. C is the energy in without catalyst. C, that's going from here to here. So that'll be an activation energy without the catalyst. D, that's this guy right here. D is our change in enthalpy. And in this case, it's a negative change in enthalpy, so it's an exothermic reaction. And lastly, letter E is the energy out without catalyst. So how much energy it loses without the catalyst. All right. On the next page, you're going to try these questions. And I am going to make a video that goes over these questions. And so try them first and then see if you get them right.